dissolve in water, right? Can salt dissolve in water? Sodium chloride? Have you seen the ocean? Yes, the ocean has salt in it, right? So yes, both of those dissolve in water, but they dissolve and then they do different things once they're dissolved. So while I'm on that soapbox, let me go ahead and get off. But here we go. So sugar, is that ionic or covalent? C6H12O6. Let's start with that. That's covalent, right? So covalent things, when they dissolve, they just get water. They just get surrounded by water. So water just surrounds them, and they just kind of hang out, and they taste sweet. So that's just how they look. They look like the sugar molecules still, but they're so spread out, can't really see them. But you can taste them if you had sugar water. But salt is an ionic compound. So when it's in dissolved state, it's actually ionized. And so that's what we're doing to our compounds today when we talk about this step down here, maybe. Right here where you said ionized or separate into ions, all soluble compounds. Only things that are aqueous or soluble, or they're in that soluble category of the solubility reserve, those are the ones that we can ionize and break into ions, where if there was something covalent, we couldn't do that. So there's a difference between what dissolve means based on the type of compound you're referencing. So let's look at these steps through a video first, and then we'll use them as we walk through an example. So this guy, he has one typo in his video, but I'll correct him as he goes. It's nice when you can correct people on YouTube. Okay.
Go
Oh wait, I'm on
on to the next one, and it's going to time you, and so it's all a lot of fun. So balancing equations is important, and it's a step that you always want to do when you're looking at any equation. And so let's go back to this Bunsen burner again. So the first thing you're going to do is observe it. Next thing you're going to do is try to describe what happens. So methane is combusting in the presence of oxygen, create carbon dioxide and water vapor.
What's methane? CH4. What's ethane? C2. 2N plus 2. H6. What's propane? C3. H8. Okay, so meth, bute, pent, and so forth. Okay, that's just quick review, but that's not what we're
focusing on. So the first thing you're going to do is observe it. Next thing you're going to do is try to describe what happens. So methane is combusting in the presence of oxygen, create carbon dioxide and water vapor. We then write the reactants and the products, and that arrow stands for yields. Next thing we do is we balance it. So we can write coefficients in the front to make sure we have the right amount of atoms on either side. And then the one thing that we should also include on a nice equation is what state it's in. And so in this reaction, we have gases combining to create carbon dioxide gas and water vapor. And so now we've got a molecular equation, and now we can use it to do stoichiometry, for example, and to make...
Okay, so you just said molecular equation. So what we've been writing our entire chemistry model so far is a balanced chemical equation, but it's actually called a molecular equation. So then he's going to walk through a precipitation example of a molecular equation, then a total ionic equation, then a net ionic equation to show how we get from where we are now to where we're going. And so you need to write down this example. I'm writing it down too. Write down your paper.
Measurements.
Before he moves on, you need to write down the reactants. Lead, and that's lead 2 nitrate. He doesn't have the 2, but it's lead 2 nitrate. That's your first reactant. Is added to a solution of potassium iodide. So you write down your reactants. See what you got first before the answer comes up. Potassium iodide. And then he even tells you it produces a yellow precipitate of lead 2 iodide. He doesn't say the 2 there again, but it is lead 2 iodide. And then you can figure out what the other product is. Just do a double replacement for me. And then I'm going to let him talk.
But now let's go to an aqueous reaction. And so in this reaction, we're taking lead nitrate, which is clear, and we're adding it to a solution of potassium iodide, and it produces a yellow precipitate. And so what we're getting is a solid that comes out of that. And so I could observe that. I could know what those chemicals are, and then I'm going to write it out. And so we've got a solution of lead nitrate, solution of potassium iodide, and it's making a yellow precipitate of lead iodide that settles to the bottom. Next thing I want to do is I want to write out my reactants and products. Now, if you don't know how to go from the name of a chemical to its equation and vice versa. I'll put a link down here to a naming molecules or a naming compounds video that should help out. So the first thing I want to do is I want to write out all the reactants and products. So now we've got lead nitrate, potassium iodide, making lead iodide, and potassium nitrate. Next thing I want to do is I want to make sure that I balance it. And so I can see right here that I don't have enough iodine on the left side, so I could add a 2 there. Now I've got too many nitrates on the left side, so now I can balance it like that. I also have to write...
All right, we good with that? Crisscrossing your charges. I'm not leaving you on nomenclature, right? Nomenclature is out in the back of your mind. You got this. Balance it with your 2s and 2s. Now he's going to say, write these states of matter. So on your list of instructions, you just wrote down for warm-up, you said, write your balanced chemical equation, and then what? Look back at your instructions. Now look at your flow. What does it say to do next? Okay, determine solubility. So what he says in the description of here is usually what I will always say as well. A solution of reactant 1, a solution of reactant 2. So if these are solutions, that term we use for that is aqueous. This is aqueous, it's aqueous. But, so you put AQ under your 2 reactants. Go ahead and do that for me. And then now we need to determine the solubility of our products using our solubility rules. So you're going to send your solubility rules someplace nearby. There's usually a stack of them on a table someplace near you. Share the love. And let's look at those solubility rules. And I know we're in the dark right now, but look at them. Tell me about the solubility of potassium nitrate. All soluble, right? All nitrates are soluble. There's not an exception. So you're going to put AQ there. AQ under potassium nitrate. And then what about lead 2 iodide? So all iodides, all iodides are soluble, right? Except for what? The heavy metals, right? Lead, mercury, and silver. So what are you going to put under PbI2? PBT, or a downward arrow, or a solid, something to indicate that it's a precipitate.
Right, the state that it's in. So remember, those first 2 were aqueous, but this lead iodide is going to be a solid. And now I've got a nice molecular equation. But again, this video is about 2 other equations. We've got ionic equations and then net ionic. And so how does that work? What is an ionic equation? Well, if you think about this lead nitrate right up here, it's not sitting in that solution as a connected molecule. Remember, it's going to break apart into its ions. It's going to have its lead ions and nitrate ions, and those are going to disassociate from one another. Those are going to separate from one another. And so when I'm right...
So this is the step that's next. You guys just said determine solubility. We did that. What's next? On your list of instructions. Say again? Ionize the ones that are soluble. And how do we indicate soluble up here? Aqueous. So the ones that are AQ, we are basically reforming their ions. We're breaking them into ions. So let's ionize these with him as he goes. And I'm doing it on the board over here, so you should do it as well.
Writing out an ionic equation, what I have to do is I have to write out all the ions. And so let's do that one first. I'm going to have that lead ion, which has a 2+ charge, and then 2 of those nitrates, which have a 1- charge. Now, why am I writing a 2 here? Because we have 2 of those nitrates. And so you can see in an ionic equation...
So this lead had a 2, you give it 2, it's 2 back. But that is describing of 2 nitrates, so that does mean you need a coefficient of 2 here, not a subscript. Good so far? Do you see that he's breaking them into ions and then describing how many ions he has? 2 for the nitrate right here?
Yeah.
So it's because if I have lead 2 nitrate, right, and I'm going to draw it big right here. This compound, PbNO32, means I have 1 lead ion and I have 2 nitrate ions bonded together. So there's this one, and this one. Can you guys see that with the lights off? Because I know there's light here. Okay. So lead, there's 1 of them. And there's 2 nitrates according to the compound formula. So when you break them back into ions, you actually do have 2 nitrates because the charges balance each other out. 2+, 1- and 1- equals 0. That's why there's no charges left on the original compound itself. So there are 2 in that descriptor of 2, that subscript of 2 is how you know that without doing this every single time. Because nobody's got time to be drawing these pictures all the time. Okay, so let's continue, and then we'll keep asking questions.
What I'm doing is I'm busting apart each of those ions. Let's go to the next one. So that potassium iodide, I'm going to break that apart into its 2 ions as well. You can see that I'm writing that this is in solution, so it's aqueous. Next we get to the lead iodide. Now remember that lead iodide is a solid.
So before I move on there, this 2, that 2 in front, the coefficient of 2, does distribute to both of those ions, so that's why they're double the ions. There's 2 of them. So what he's going to say is, this is a solid. We don't touch the solid. We keep exactly.
It's a yellow solid, and so I'm not going to bust that apart into its ions. I'm just going to write that as lead iodide as a solid. But then this potassium nitrate is going to break apart into its different ions, so I'm going to write it out like that. So I know that's a lot of work, but this is a complete ionic equation. Why is that important? It really allows us to look at what ions are in that reaction. And so if it's ever an aqueous reaction, lots of times we'll use this ionic equation. Sometimes I'll call it a complete ionic equation because it's...
Okay, so we've got this complete ionic equation. We basically represented them as actually how they exist in their solutions. This is all in water. This is all in aqueous solution. So that's why I'm making it have ion charges. Do you remember earlier, like for I by itself, we wrote diatomic iodine, I2? That is no longer the case only because this is in water, whereas all these other ones we were doing, those were just in the air, those are on the lab station, they're in nature and everyday life. This is in water. So, who watched the volleyball game last night? Okay, so we got a couple of people watching. Did you guys play volleyball game? No, right? You were sitting there watching, right? So, over the course of before the game started to after the game ended, you were just chilling, sitting on the bleachers. You were doing some other stuff, but you didn't really change. But the people playing the game, they're the ones actually playing the game, they're involved, they're making stuff happen, scoring points, and what do you call it when you're spiking it? They were doing all that stuff. You were just sitting there. So what would you give the name, if you had to give a name for yourself, what were you in that whole arena? You were spectators. You were just big chilling, right? Okay, who is my spectator in this reaction? Who's just big chilling and does not change from beginning to end? Who looks exactly the same? 2 potassium ions, same, they're spectator ions. Who else? Nitrate, big chillin', doesn't change, okay? So, who are the game players? Who are the ones that are in the reaction? Pb2 plus and iodine, so I2 are 2I, 1 minus, and they make something happen, right? What are they making happen? You're just mumbling to me. Say again? This ionic compound's forming. They're coming together and go like, yeah, let's precipitate, and then they precipitate, and that's the reaction, that's the game. They made something happen. So that's the term spectator ion. What you should always recognize is that, just like in everyday life, spectators, they don't do anything, they sit and watch. So nitrate and potassium, they don't do anything, they sit there and watch. All right, let's finish this up, and that's now going to lead us to our net ionic, our final step.
Showing all of the ions that we have present. Okay, what's the third type of equation? That's going to be the net ionic equation. So if we look back at this equation, you can see that we have 2 nitrate ions on the left side, and we also have 2 nitrate ions on the right side. And so they're really not being changed in this reaction. And so we call those spectator ions. They're really just watching. And so what you can do is you can cross out things on the left side that are also found on the right side, as long as they're in the exact same form. Can you find something else on the left side that's also on the right side? That's going to be those potassium ions. So I can cross those out as well. And so once I've crossed out all those spectator ions, I can write it out like this, and that's going to be my net ionic equation. So that's really, it's just showing what atoms are part of this chemical reaction that are actually forming these bonds.
And that's a solid.
This will become important when we're looking at redox reactions in the front. So now once you've got those equations, so this would be a molecular atom.
Okay, so the last step is just rewriting the equation with only the parts that matter, which are the ions that are doing some action and causing some changes to occur. So this would be your final answer with your lead 2 plus 2 iodide ions making lead 2 iodide. But it does take some work to get there. So don't jump straight to the chase. Don't jump straight there because you'll make a mistake. And they do get a little bit more complex. But you know how to do this. You understand that there's a separation occurring through ionization, except for the thing that's a solid precipitate. We didn't touch that. And we came down to our final net ionic. Give me a thumbs up if you kind of feel like you got the process a little bit. And you have your subs. Okay, you put your thumbs down. Thumbs down. I can see that we need a little bit more. So let's do one more together. But these are your steps, right? Do you understand how these steps correlate to what we did? Yeah.
What I'm just really not understanding is how do you determine if it's a precipitate or a solid or a gas, or how do you determine which element?
So we're going to use this for double replacement reactions, your solubility rule, to determine if it's precipitate or not. But for everything else, if if I say solution up, or if I'm telling you right now everything's a solution in the beginning, you put AQ and AQ. But remember, these are all, what I've said to you now is these are all in aqueous solution. These are all in solution. There will be no gases because we're all in solution. We're not like in the air. But in terms of like old stuff, synthesis, decomposition, single replacement, and combustion, a lot of those, if you can see the formula, you can tell it's a covalent compound. Covalents generally are gases at room temperature. Not metal, not metal. Generally, ionics are solids at room temperature. So this is like old basic knowledge from maybe when we started like ionic and covalent talks. And then single elements by themselves, if it's a metal, it's a solid. If it's a non-metal, it's a gas. So based on like the stuff that you learned initially. And I'll kind of hit that with review as we go.
So you just have to as you get to okay, it's a solid.
As based on it's like identity. Yeah. Question, Greg?
Yeah, so we didn't have to like balance at the end in that example.
Because it already was balanced.
Well, otherwise, we would normally balance if we had to.
If we keep it constant, like, we're carrying the 2's down as we were supposed to, we shouldn't have to balance at the end. You just need to double check that it's balanced at the end. We should be consistently balancing as we go. There shouldn't be a need to rebalance anyway. So I'll show you guys another video if I can at the end to give you some more indication of what's happening in the switch. Let's do number 2 here. So you guys write down the reactants, do your double replacement. And I'm telling you right now, double replacement, are you cool with identifying that that's double replacement? Based on that two iron compounds coming together? They only have one thing they can do, they just do a little switcheroo. So write down your reactants and products. No, yeah, so starting with magnesium chloride one, that's number 2. So take you just another second or 2. 5 seconds are longer. Like I tell my husband I'll be home in an hour, I'm home in like 3 hours, you get a little bit more time with that. Give me just like a little thumbs up if you got magnesium chloride so far. Sydney? Put Sydney on the board. Sydney, you with me? That's sodium phosphate. There is a P in it. This is phosphate, not phosphide. How's got you? PO4. Okay. Charge of phosphate. Anybody? 3. So crisscross the 3 down. Crisscross the 3 down. And then sodium charge 1. So leave it as is. Okay. And remember, your double replacement is a positive magnesium and a negative, in this case, phosphate will come together to make magnesium phosphate. You just plop them together like that. Is that good? What do you have to do? Crisscross charges. Okay. So 3 from phosphate goes down, 2 from magnesium goes over, and last one is what? Thank you. Sodium chloride or NaCl. Do not put ClNa. It looks dumb, right? It don't look good. If it don't look good, do a double check at it. Make sure you've written it correctly. If it looks like something you've never seen before, you probably haven't seen it before. Yeah? Yeah. Yeah, it doesn't matter. As long as the compound's correctly written, we're good. Okay, so then to balance it, we need to do what? Well, hold on. We already crisscrossed these charges. That's a 1. That's a 1. Good. Where do I need some numbers? 3 in front of the magnesium chloride. Okay, that makes 6 chlorines. Uh-oh. 6 in front of sodium chloride. Okay, that makes 6 sodiums. And 2 in front of sodium phosphate. And are we good? Yes. Think of phosphate as a happy family. There are 2 phosphates there. There are 2 phosphates here. We are good. All right, step 1 was to balance. Step 2 is to do what? Solubility, states of matter kind of thing. And I'm telling you at the beginning, there are always 2 aqueous solutions given as reactants. Because if not, the reaction won't really occur. We need to have something to like kind of pour together to make a reaction occur. So I'm telling you right now, these are 2 aqueous ones. Don't even look at their solubility. That is a given right here. Put AQ for yourself because that's how you're going to know ionized or not ionized. Okay, next solubilities. What's the solubility of chlorides? This is not memorized. You're looking at a sheet. All soluble?
Except for
So there's heavy metals, but is this a heavy metal? No, this is an alkali metal. All right, so this is aqueous because it's in this soluble category. What about phosphates? All phosphates are insoluble except for alkali metals and ammonia, right? So that's not the case. So this is what? PBT, right? And I'm just going to put downward facing arrow for PBT. That means solid hits bottom test tube. All right, next step. We've gone balance, we've gone solubility. Ionize, which ones? The aqueous ones. Okay, you guys tell me, what's the charge of magnesium? Breaking these up. Charge of magnesium? So there's 3 magnesium ions. How many chloride ions? 6. 3 times 2 is 6, right? So that's 6 chloride ions. And then sodium phosphate also gets broken up because of the ionization here. How many sodium ions? 6 sodium ions. So that's 2 times 3. And there's 2 phosphates. Do not break up phosphate into its individuals. It is simply phosphate. How many phosphates are there? 2, right? That 2 distributes, so that's 2 phosphates. And these are all aqueous. AQ, 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 and AQ. These little squiggly lines are Qs. Okay, so we got our AQs written out to signify it's still aqueous. And as we create our products, we need to look at solubility. Do I ionize this one? I see one person saying no. Can I get some ingredients? Okay, so this is a solid precipitate, right? Do not touch the solid. Do not break it up, meaning just write it as is. Mg3PO4 2, and just put a little PPT or solid underneath there to indicate that that's together. And then what about our last one? So yes, this breaks up into 6 sodium ions and 6 chloride ions. So if you're not putting the charges, you're doing it. You're not putting your ions, and this is a net ionic equation, so we need to have some ion charges on there. So now we're kind of towards the end. Who do you see? That is a spectator, meaning they have not changed from beginning to end. I heard sodium, so the 6 sodium ions cancel. The 6 sodium ions cancel because they are exactly the same from beginning, and then they didn't change. No chemical changes occurred with them, so they're spectator ions. And chlorine, same story. They don't change, they get cut out of the equation. So then who's really reacting here? 3 magnesium ions and 2 phosphate ions, and then what are they doing? They're making, what's the name of this? They're making magnesium phosphate, right? So, can you see the purpose of this at all? It's okay if you don't. Who feels like they do? So, Sheena, tell me why we're doing this. What do you think?
Just shows you what's truly reacting in the equation and what not.
Right, so what matters in this matter is that there's this one ion and this one ion, and when they get in contact with each other, they make stuff happen. They make a precipitate happen. Because if nothing happens, this whole thing was a waste, right? If nothing happens, we call that a no reaction, right? So if no precipitate occurred, it would just be like liquid, 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 right? You don't see anything happen. So we call that a reaction, but in this case, something did happen, but we don't know what's causing it to happen. And it's just these 2 ions in particular forming an insoluble product. Everything else is just there for the ride. But they have to be there because I don't have just straight up magnesium ion. I have magnesium, but I don't have magnesium ion. So I can't just give you the single ion and go, okay, react them. So they come in forms of ionic compounds. Question?
Got it.
Okay, great.
Yeah, wait.
No, okay.
So precipitates are considered solids. And once they're solid, you cannot separate them into
Ions again. you could do like a lot of other experimentation, but we wouldn't in this case. Okay.
And also, with double replacement, you always just flip it. It does not matter which one tracks or like the single replacement.
Yes.
You just flip flop no matter what.
Yep, because they have another partner that's going to be bonding with them regardless. Okay, let's pause on this for a moment, okay? Let's go back to cars. And I did not finish passing these out. Jacob's going to hold up one, and you're going to grab it. Thanks, Jacob. And I do need them back, okay? Don't steal them from me. I need them back. But we need to go put them outside. So here's what I need from you. You're going to talk to people in a group. So if you need to get with your car person, get with your car person now. Do it now. And I'll tell you where we're going next. All right, get with your car person now. And I'll just tell you what I need from you. This will take us about 5 minutes at first. Thank you. All right, get with your car person in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay. Touch, like, just make sure your shoulder's next to them so I know, like, who you are. And then I need you to pick another set of partners that you're going to share with. You're going to pick them with your eyes. Okay? You need to claim them with your eyes. You need to give them that look that I am yours. Okay? All right. Has everyone claimed somebody with your eyes? Just give me a thumbs up if you've claimed them. Okay. These are the conversations you're having. And then at the very end, you'll see it says, tape the molecules with a string onto the car outside of my room. I will facilitate that. But you have 5 to 10 minutes or so to talk. I will say 5 to 8. Yeah, 8 minutes to talk with both parties. Can you guys see everything? Yes. Share your wisdom with each other. I'm not going to have you write anything down unless you're just off task. Share your wisdom. Go. Do you have a presentation you would like to pull up? Yeah, that's fine.
Yeah.
Okay, ready? So we did.
We don't actually have like a
That word. I think to left the list, to left the list. Okay, anyway, so this is apparently
yeah, that's
it's not for so to say it's right? These are
That's great.
like there's a lot more parts of work and or I mean see how there's 1, 2, 3, 4 it says like it's larger inside so we're talking to plastic so it's like really high Oh, yeah. We just pull it with, yeah, what's the idea? Is it over there? It's right there. It's right there. Don't touch it. She'll kill you. Since you really don't like it. It's right there. It's on the top shelf.
What are you looking for?
It's right there on the top shelf.
It's in the coffee mug.
Top shelf.
No, it's in the coffee mug.
Oh, that's what I meant.
That's just a Geo.
That's what I meant. Dude, I saw it sitting down, so I just saw it beside for a while. It's not my fault.
I remember where you were like, I saw it.
I don't want you to
If you are done sharing right now, please bring your colorful paper out to me.
Alright, I'll do it right. It's not round, but I want to play this game, but we never played. I got cake too. I got cake. I got cake. Yeah, I can't hear you one.
What's his name? Oh, she has little island right here. I'm terrible. She probably won't have it right here, but it'll blow up.
3D printed.
Yeah. Oh, I see it now.
Are these 3D printed?
No, those.
Yeah, this one's 3D printed. You can tell. Because it's got the
Oh, yeah,
back
yeah,
and
yeah.
forth. Aw, but it broke.
broke like 4 times, 3 times.
Too cool.
That worked out some.
You're too cool.
Right too, you see it's sparkly?
Sparkly?
Look how sparkly.
She shook it and I was like, what if it just
Yeah,
blew
it's,
up right now?
it's also carcinogenic, so I have to keep it contained. Please don't take it too hard, because I did have somebody drop it last year, and it spilled all over the floor. And then I was like, it was one of my AP students, so I said, you have a year to make me some new. It's called Golden Rain. It looks like Golden Rain, and he had to make it for me at the end of the year. So I was like, that's mine. That's like, that's just like so cool. So he had to make me some more, and then we had to like decontaminate my room. It's a unit cell. We had to use a special cleaner. All right, so you guys are gonna work on. Well, yeah, it is 3D printed. We're gonna work on. Yeah, I have a friend who works in 3D printing industry. So I was like, can you make me West Nile virus and RNA and a unit cell? So, you guys gonna practice these while we wait on the rest of the crew?
Oh, I forgot to show them
What's
polymers.
this?
Yeah.
It's a stapler.
Practice the two that are, practice the first one that's on the board. Practice the first one that's on the board.
Oh, I don't want to do anyway. What's this?
Thank you.
What's this? Oh, a paper clip thing?
Polymers.
What's this?
Oh no, there's yarn on my phone.
Well, you see, stress.
Nope. Nope. And then it's healed to become.
Yes, we have a lab. But I can't let you go to the lab until this one is very successfully done. People are gonna be wowed by our car, guys. I've already had people make comments.
Really?
Good comments? Good, yeah. Positive comments. They're like, that's so interesting.
My question is for the sodium hydroxide. This is compounded. Considered soluble compound.
Some teacher, right? I always forget. That's an R. That's an R. How do you look for SP? No, I found it. not, are they? Oh, strontium is. Oh, no, that's why I wanted to do this one. I was like, why did I do this one if I saw it? Okay, I don't have my solubility rules in front of me. So, you guys made it this far, right? And you were like, okay, I got my solubility rules identified. All hydroxides are insoluble except for who? Look at your slate. Okay, pause. Whoa, pause. The very first one says all hydroxides are insoluble, meaning they all form precipitates, except for who? Let's start with alkali metals first. Where are the alkali metals? First group. Okay, because sometimes people still put sodium hydroxide as insoluble, meaning precipitate. No, it's an alkali metal. And then the other exceptions are strontium, barium, and calcium, right? I call those CBS, calcium, barium, and strontium. So this one's our aqueous one too. So what do you say about this reaction? No reaction, right? Because guess what? If everything's aqueous, what are we going to do to all of them in the next step? Break them all down into ions, and then what are we going to say about all the ions? They're all spectator ions. So then, is anybody playing the game? No. Is there any reaction? No. So don't let yourself go through all the work and go, oh dang, got all these ions, I cancel them all, and I say they're all spectators. If you can realize that up front. And that's why I heard someone go, they're all aqueous. I was like, they've realized now what the purpose of this is. So there's no reaction. So theoretically, on paper, you can write any reaction. But does it actually occur? No. Okay. So we have 7 reactions we're going to do in the lab. And those 7 reactions, there's this 4 double replacements and 3 single replacements. So what I want you to do is I want you to pace yourself. I want you to do, let's write. I'm going to ask for you to start with writing 2 reactions. And then you'll do 2 reactions in the lab. You'll write 2 reactions. And you'll do 2 reactions in the lab. Got me? Kind of pace yourself so you can see that you can write on paper and you'll try in the lab. However, let me get you started because these are pretty, the laboratory setup is kind of complex. There's like 10 reagents back there per lab station. So to make this kind of seamless, I'm going to have this group over here. You guys are going to do 1 and 2. Start with 1 and 2. This group over here, 3 and 4. Starting on reactions 3 and 4. You guys are starting on reactions 5 and 6. Okay, let's start like that so I can stagger you so I can help you guys in different places. Because if we don't get to all of them today, I can still actually have you guys demonstrate for other groups. Because you're going to ask us that particular reaction. So, I did not demonstrate any studies for single replacement, but if you got the flow and you know how to do it, I think you'll be okay. So let's go ahead and start writing reactions in our seats and then we'll get into the lab. Write our reactions in our seats and then we'll go to the lab. You're right now doing, for now doing reactions 1 and 2, but you'll get it.
Oh.
So that's not copper 2 right there. Compound or copper 2. No, it's not.
The first two are always yeah, SO4 is usually soluble except for
Oh, okay. I was confused.
yeah, and then once you react,
Copper is not so much, so that means that you replace with yeah, you replace the copper with switch copper. Yeah, yeah. And what happens at AG? Yeah, so it'd be A plus CU. Yeah, so it's like that. Wait, no, it's
all you gotta do is put
that means you have to put two here, so then you have to put two AG to balance. I didn't even hear So I guess
The first one, we have three in front of the sodium hydroxide. And three in front of the
yeah.
And then the second one,
You just gotta put two in front of
does
the
ammonium have a charge? Or
yeah, just put it there. That's the balance. So it's out there.
wait, it says right here, replace hydrogen. What are we actually going to do? So then it can also
I think the only ones that change.
yeah,
There's a reaction.
oh,
Hey, no. Yes, no reaction.
yeah, we'll go back to the lab.
Alright guys, let me get your attention so we can kind of move back and then see what's happening here. So I basically told most of 1 and 2 reactions, most of them are going to go to the front. 2 lab stations are there. There's like a lot of it, there's a lot of reagents out and everything, so kind of we might move some. These 2 tables are generally going to be going to this middle table here, if you guys can see it. And then these 2 tables are going to go here. you probably want to go ahead and claim a group of 3 to 4 to kind of work on together. So your table groups might work really well for that. When we go to the back, you need to read the instructions that are before your reactions. You also need to read the reactions. Make sure we get the right one. And I want everybody now to tell me how much are you putting into your test tube. So we'll get instructions in. 1 milliliter. And what you will see is you guys, and this is very, very important because there's, I don't know, thousands of dollars of chemicals. And as I prep these, I prep them carefully to make sure they're not contaminated. Your pipette must be clean. So get a beaker of water, pipe it up and down into the water, clean it out. And then on here, you guys can't see really from where you're sitting, but there's little etched lines, and it says 1 milliliter right there. So you don't have to use a graduated cylinder. You can use this exactly to get what you need, okay? So you do need goggles on, you need closed-toe shoes. Come on, we got 20 minutes. Let's go.
I just don't know. They cross out there. You cross out all over.
Reactions 5. Okay, reaction 5. Alright, reaction 5 is and it's silver nitrate. Make sure you keep that. Do that. It's that kind of a brownish bottle. Okay, so make sure you have that. And then also your metal pieces, I'm going to bring to you in a second. I'm putting really strong aspirin. So people do not knock it. And I do think this is I need like maybe 2. Actually, we're going to start on the number 6. I dropped you back there. You guys are good. Questions. Guys, if you are going to begin, please go ahead. You need to be respectful and read the instructions. Alright, let me demonstrate. You very carefully. You have 6 more hydrochloric acid. I don't want this to be spilled. So what I do first is let's talk about the process of what you're doing. I'm doing this very quickly so we can get started. Team, you ready? Okay. We have at least one person listening. We have a test tube, and your test tube is spaced out. We have a pipette. You're going to get 1 milliliter of acid, and you're going to put it into the, just wait 1 second there, so you get put that into your test tube. And then you're going to get some blood flow out of your drawers, and you're going to get some mossy zinc. And then after you put your mossy zinc into your test tube, what you're going to do is allow, do you have it? So this is the test you're sitting in your eye, sitting around, you're not holding it. You're going to allow the gas. You might put 2 pieces of zinc in there, maybe even double the gas, just start the gas going to zinc in it. You're going to invert this test tube, and this is called a gas collecting tube, to collect the gas. Keep the gas collecting tube there until the gas works, until it's going to fill the gas, and then that's still the test tube right there. Then you just kind of take this off from the top, and you're going to stick this line down to the board. There's a lot of stuff going on. The dumpster is on fire. You're going to hold it underneath the mouth of your test tube and make noise. Right. Okay. Now, go slow. Make sure it's coordinated. Gas collecting tube. Gas collecting tube. Go straight up until you're ready. I don't even have a circle. Alexis has the thing. Make sure you know you're ready for everything.
It's like four, okay, make sure it's tighten it all the way down. And then it's like,
Okay.
what is it? Wait, you got it already? The bottom might not be.
Everybody be quiet for Black Court. 3, 2, 1. We're gonna listen to this one. You guys ready? Never mind, it's slow. Never mind, they're not ready. Alright, so you guys can do your other reaction. Let me get your property. You can do Listen, 5, 4, 3, 2, 1. Woo! Okay. And that's it. That's all the Heisenberg does. What it is. So speak your water. Speak your water. You guys need to you got a long stick. I'm gonna get you guys some popcorn. Now, you can go ahead Alright guys, after you read your reactions, you can continue writing reactions out and completing the rest of the lab. Guys, we have about 5 more minutes, so if you're working on a reaction, get that reaction done. But you will finish all the reactions on your paper, no matter Is it reacting? It's So guys, we have 4 minutes. Do you see this filter paper over here? Now, all the solids that are in the test tube to go down this filter paper, all set up another one. No solids on the sink. If you have silver nitrate, be careful with silver nitrate. It will kill your cells and turn your hands black. If you have anything else, do you see, be careful with, but you need to wash out your test tubes. Get your precipitates going in here. The ammonia, the pee, everything, the yellow drain, that's where you go. Clean up everything. I'll see you in the in 3 minutes.
underneath we have I would call it No, it's only that. You accidentally. It wasn't accidentally.
I'm tutoring. You can do it today.
I can? Alright. Maybe like 2 minutes.
Hey.